My name is Ryann Fortner, and this is my Physics 2211 Lab 4 on oscillations. Firstly, I'll go over the purpose of the lab and the key concepts. Then I will analyze the data taken from Tracker, and then I will create a computational model that models the change in energy versus time and the change in position over time. Then I will answer some relevant questions about the data. The purpose of this lab is to examine the motion of a mass attached to a vertical spring oscillating when the spring swings in an arc, and relate my observations and computer model to the energy principle. In the end, the observed data and computer model are very similar and agree with the energy principle. The first key concept is Newton's second law, or the momentum principle, which states that an object in motion will stay in motion until influenced by a force from its surroundings. Using the variables definitions and the key equation, we can manipulate this law to compute the expected velocity or position using the equations below. Our second key concepts are spring force and oscillation. The spring force is equal to the negative spring constant, Ks, times S, where S is the length of the spring subtracted from its relaxed length. It is a non-constant force. Oscillation is related to the internal up and down movements of the spring. The time period of a single oscillation is represented by the equation T equals 2 pi times the square root of m divided by k, where k is the spring constant. The last key concept is the energy principle, which states that the energy of the system is equal to the work done by external forces plus the loss or gain of heat by the surroundings, where, depending on the choice of system and the surroundings, delta E equals delta K plus delta U plus delta E thermal, or kinetic energy, translational and or rotational and or vibrational, plus the potential energy, gravitational, spring, or electrical, plus the thermal energy. The work done by external forces is given by the force times the displacement caused by that force, or for non-constant forces, the integral of the force found at the initial and final positions. For this lab, only kinetic and potential energy are important. Work in this situation is zero. The only specific energies that we care about for this lab are K translational, which is equal to 1/2 times the mass times the velocity squared, the potential spring energy, which is equal to 1/2 times the spring constant times S squared, and the gravitational potential energy, which is equal to mass times the gravitational constant times the change in y. Using the pre-lecture video given, our system is the spring plus the mass plus Earth, and the surroundings are nothing. Initially, the mass and spring are motionless, the mass equaling 0.402 kilograms, and the spring constant equaling 6.83 Newton meters. Using the spring force equation, we also found the relaxed length of the spring is 0.123 meters. Pause to read more carefully. Here is my calibration of the tracker video. Using tracker, I found the X and Y position of the mass during the video, and I took this data and copied it into Microsoft Excel for a .csv file to use for the computational model. For the computer model, I firstly entered in all of the constants, initial conditions, and initial equations for energy. Then I calculated the net force and the velocity and position update formulas for the mass and the spring. Then, using my initial conditions, I calculated the final energy at each position of the mass. For the graph of energy versus time, you can see the total energy is constant, while the delta K, delta U grav, and delta U spring all oscillate. My observed position data is also very close to my computer model position data. For the model, I did not account for other external forces like air resistance. There is also possible human error present in the observed data because of the video quality and my own difficulties using the tracker software. I also don't account for other factors in energy loss for the model because of how negligible they are in this scenario. For the first question, is the energy principle satisfied? Our answer is yes. Since there are no surroundings, the total energy is zero, which is consistent with the orange line on the graph. Since the mass slows down as the video plays, the kinetic energy also decreases, which is consistent with the blue line on the graph. The potential gravitational energy and potential energy of the spring are inversely related to each other with roughly equal magnitudes, since the overall net force is again equal to zero. They oscillate within the same time phase, just in opposite directions. As one increases, the other decreases the same amount. I also compared the time it took for one oscillation to be complete in the x direction and the y direction, and they are different. This is because the mass is moving in two different directions with two different behaviors. In the y direction, the mass is moving like a spring, but in the x direction, the mass is moving like a pendulum. Thank you for watching my presentation.